Okay, so let me introduce Professor Hlaváč and his robotics and machine perception department, and let's go.
Okay, so I'll be brief. Sorry for that. My Zoom crashed, so this is what you see there. So we have in robotic machine perception department, which I'm responsible for. We have now 4 groups: robotic perception, intelligent mobile robotics, applied geometrical algebra, Tomáš Pajdla and Thorsten Sattler should be written there. And the new group named Impact by Josef Sivic, you see the number of people. For the performance for brief, I choose only one measure, which is from V3S, which is the system for evaluating scientific results at the Czech Technical University. So they are counting in points. So 630 points is the amount of points, 1,000 points, which is second in CIRC from the departments. The first is Zdeněk Hanzálek, one for the year 2023. And third after us is Foxes, where you can see there is a gap again. In terms of citation, our department is in the first, so there is 341,000 points for citation, which is an order higher than the other departments. So and then we start now presenting one by one. The next one is Karla Štěpánová.
Hello, everyone. My name is Karla Štěpánová, and I will present our paper, which was last year published in Robotics and Automation Letters. And the paper is focused on imitation learning dataset for training and evaluating 6D object pose estimators. And why we selected this paper is because it shows also collaboration between different teams within CERC, namely Robert Babuška's group, Josef Sivic's group, and Václav Hlaváč's group, RMP. And the main author is Jiří Sedlář, and I was the second author. Our aim was to find out if current vision methods are good enough to already learn from humans just based on camera data. When we put the camera into industrial setup and we record a human performing some tasks like gluing, drilling, and whatever, if we can learn the parameters and the movement of the tool which is used. And we found out that the current data sets for vision methods are not good enough to evaluate these methods for these industrial setups. So we simulated real-world industrial use cases and their usual demands on the 6D object pose estimators, like that you have heavy occlusions, you don't have the model of the object which you are using the tool, because the tool might be anything. You want to perform some task using battery, and in that point you don't want to be dependent on having it beforehand. And you want to just observe the human performing the task, extract the data from that, and then basically transform it to robotic environment and perform it by the robot. The data set covers currently 10 different tools which are recorded by different cameras. We have variability across the manipulating hand, left and right hand. Also, the demonstrators were varied, and we were varying also if we have the cluttered or non-cluttered environment. And additionally to the dataset, we were also publishing methodology, how you can easily extend the dataset for new objects. So that when you are in your industrial use case and you want to use different type of drill, you can just easily track the drill, get very quickly the model of the object, record a few seconds of the data, and then use it for training the estimators. Here is an example of one of the tasks which was performed, and we had several different tasks ranging from gluing to drilling or wiping. And the training data set is consisting of, as I said, just few seconds of recording of the tool in front of the green background, which enables separation of the green background and augmentation, which proved to be very crucial for generalizing to different setups and different demonstrators. And we also published our improved augmentation methods, which enable this generalization. And the test set you saw already different tasks. Ground truth to measure the quality of the estimators was provided by HTC Vive tracker. And we also showed the results of the baseline method, which was a dope 6D object pose estimator from 2018. And it's a method which doesn't require the model of the object, that model. So that's why we used it as an example. And we proposed several tasks which should be evaluated for different pose estimators, so that you evaluate how the method behaves when you try to generalize between different camera viewpoints, between hands, between the demonstrators, and so on. And finally, the results show that, as I already mentioned before, that the augmentation is crucial to achieve reasonable results. When you don't use any augmentation, you get approximately half as good result, like only 30% pass rate, compared to 60% if you use our proposed augmentation method, which is a mixture of random backgrounds and the blending with the original setup. So you take a bit of information from the industrial setup, but also randomization of the background. However, the DOPE method, which was the baseline method, reached only 20 degrees rotation error and 6.5 centimeters translation error, which is not good enough for real robotic application. So you see that there is enough space for improving the vision methods to be actually applicable for this type of task, so that you can just track a human manipulating the tool and then transfer it to robotics environment. We don't expect that these estimators would be good enough for precise manipulation, but they should be good enough to be used for tasks where you, for example, are gluing and you are fine with half centimeter error or stuff like that. The data set and the code are available online, so if you are interested, you can check it. And just last few words about me. I'm involved also in Imitation Learning Center, where we are focusing on human-robot interaction and communicating tasks by language and gestures to robots. And we had a few other publications last year, especially about how to communicate by gestures, which was done mainly by my PhD student, Petr Vance. And if you are interested, just check the websites for more details. So that's it.
So, good afternoon, everyone. My name is Woller, and I will present our most recent journal paper, which is called the Hamiltonian cycle and traveling salesperson problems with traversal-dependent deletion. This is a result of our ongoing collaboration with our partners from the UK. Two of our co-authors are from the University of Birmingham and one from the University of Oxford. And so far, we've produced the journal article I'm presenting, which was published in the Journal of Computational Science. Then we also did a workshop at the ICAPS planning conference in Prague last year. We have the paper at the ECMR Robotic Conference, and currently we have a follow-up paper review for the ICAPS London Planning Conference. So this research is motivated by practical application from autonomous open pit mining, namely the drill and blast method, which consists of phases. In the first phase, you need to drill a dense pattern of blast holes, and this actually was the problem that we interested in. And the problem is that as you drill the blast holes, you generate piles of excess material, which continuously fill the environment with obstacles. Here's a view with multiple drill rigs. And then in the second phase, which we don't actually study, you fill the blast holes with explosive and there's a nice explosion like this. So based on this, on the first part, on the blind problem, we proposed and studied three directory problems. First of which is the TSP on self-deleting graphs. We introduced the concept of some self-deleting graphs, which are simple graphs that have vertices and edges plus a delete function. And the basic idea is that once you visit a vertex in the graph, you delete a predefined set of edges in the graph. Then on this on these kind of graphs, we formulated several optimization problems, variants of the Hamiltonian cycle problem and the traversal-dependent problem. We did several proofs concerning properties of the graphs and the solutions to the introduced problems. We proposed an exact solver and also a more scalable materialistic solver, and we also performed statistical analysis of Hamiltonian bound. The second problem we proposed is called path conforming circle placement problem, which is formulated as follows: given possibly optimal path with an environment, we want to place circles of maximum radius, so that each time you visit the vertex, you have to, or you want to place circle right next to it. And the goal is to find such a placement that the common radius is maximal and that your path does not traverse through already placed circles. So again, we had some both theoretical and practical results. We derived some lower and upper bounds of the problem. Then we proposed a heuristic solver. And finally, we combined both of these problems in the third one, which finally solves the originally proposed motivation. And that one is called TSP with circle placement, where we address simultaneously optimization of the path and placement of the circle obstacles. We propose to make another materialistic algorithm combining approaches for the TSP on self-deleting graphs and for the path conforming circle placement. And we also extended this approach for the Rubin's vehicle. So it's the end of my presentation. Here are some visualizations and acknowledgements. Thank you. Thanks.
No questions?
Oh, I can do a quick one. Can I ask a quick question?
Sure. Don't ask.
So given what Przemek was showing, thinking about the machine learning these algorithms.
So what was the question? If we did think about it, or
Are you planning to try some machine learning to help this algorithms?
Well, not in the short horizon, but we know about the simulated. But
it's not in the current algorithms. And
so welcome everyone. My name is Košnar, and I want to apologize for the font replacement. PowerPoint is not really portable format. And I want to present the application result, which was achieved during the solution of the project research and development of a robotic system for automated masonry for Playbox, funded by Technology Agency and Ministry of Industry and Trade. So the main goal of the project is to develop a robotic system which are able to autonomously build a wall from the clay bricks, where the speed of the system will be comparable or better than the human worker. And part of the project was also the development of the specific clay brick for the robotic application, which is called robot-ready brick. So this robot-ready brick is covered by the existing patent. and the rest I will introduce more. So project participants is Wienerberger, KM Robotics, and two groups from Czech, IMR, Intelligent Mobile Robotics, and RMP, Václav Hlaváč. And the main goal of the CIRC in the project was to implement the detection of the elements which are used in the process of wall building. So detect the bricks, detect the pallets of the bricks, detect the already built wall, and detect if the foam, which is used for the wall building, is properly applied to the brick, because there is no mortar, there is the foam which acts as a glue. Second goal was to implement the planning system, which planned the movement of the robot and lay down plan for the individual bricks. And there was also the help with the analysis of requirements and implementation of the gripper for the robot and for the implementation of the system in the robot operating system. So here is the example of the detection. For the detection of the bricks, it's used the laser rangefinder. Very hard problem was to detect the grooves, which are used for the gripping of the brick, because the grooves are very shallow, so the measurement was not so distinguishing from the noise. Other part is the detection of the bricks on the pallets, so you don't want only to detect the pallet as a whole, but you want to also detect the individual bricks how are already used from the pallet. And the fourth image is the detection of the foam, which is already on the brick. So you want to see two lines of the foam. If one of the line or both of the line of the foam is missing, it's not enough to build a proper wall with the enough strength. So you don't want to avoid this. So I show you two short videos. So here is the planning of the laying the bricks according to the position of the robot and the possible reach of the robot. And what was the main challenge is that the bricks are not all the same size. The variance of the size of the bricks is up to 1 centimeter. So if you lay 10 bricks, you are almost half of the brick away. So you need to plan with this to keep the overlay of the bricks, not to build the columns, and also you need to adjust the plan for actual state of the wall. And the second part was the planning of the movement of the robot. So you want to have the movement as optimal as possible, because you want to be as quick as possible. And there is three types of the movement: detection of the bricks and the grooves, applying the glue, placing in the correct place in the wall, and then return back. And now I will show you the speed up video. It's about 1.5 minutes. So at the beginning, the robot scanned the pallet and scanned the individual rows and individual edges. Now the robot detects the laser plane, which defines the position of the wall. And then the small movement is for detecting the grooves, applying the glue, and then putting the brick in the wall. You can see that the robot is able to grab two bricks at once, if it's possible to place it both in the wall. There is not enough space, the robot takes only one. Also, if the position of the bricks in the pallet is not good enough, like there is a gap, the robot is not able to grab two at once, it's able to operate one by one. And you can see that the robot is also able to build the wall. There is some opening for doors or for the window. Now you can see that the robot is able to move by itself, like walking, and then use the second pallet to build the rest of the wall. So I think for the illustration is enough. And now for the commercialization, the main partner, the Wienerberger, use this robot for offering work as a service. It means that you order that you want some square meters of the wall, and then provide you the bricks, provide you the foam, and provide you also the robot. Lend you a robot which is able to build the wall. Already 7 robot units is manufactured and prepared for deployment. And actual speed of the robot is approximately 10 square meters per hour. So it's something like twice as quick as the manual worker. And the license for this solution, for our part, for detecting and planning, is already sold to the Wienerberger and KM Robotics. So if you have any questions, thank you for your present
You can deal with different types of bricks, because typically on the side it's smaller brick, or window side is different.
Yeah, now the system works with only one type of the brick, and all these half bricks and half is played by the human worker. So there is some tablet which you say, okay, I need to place this type of brick or this size of the brick to display them. So
Thank you. Thank you very much. The next speaker.
So the next presentation will be Antonin Vobecky. I just want to say a few words before when he installs about the next like the line of the presentation in his department. It was great to see lots of journal publications, and it's great that people are really sort of now conscious of what platform they use, if it's a G1 or G1 journal. For the rest of the presentation, for this department will be conferences. So we discussed with Zdeněk a little bit. It is also important to think what are these good conferences or not. I just want to say these are computer vision. In our case, it's going to be Tomáš Pajva, Professor Sattler, myself. You'll see, I think, 6 presentations. They are all top-tier conferences in computer vision and machine learning. And what's important to know that that's where the action happens. So this is in those areas, the conferences are at least as important as the journal publications. So you're going to see conference publications. And about the 2 next presentations, first one is Tonda Vobecky. It's a collaboration which we had with Woller AI Research. So it's an example of a joint work with the industrial research lab, but on a problems which is kind of 5 years away for them. So it's going to be really like published at conferences on interesting problems about cars that they could eventually learn by themselves. And the second presentation is going to be Anton Bušev from my team, and it's a completely new direction which we are looking at machine learning for protein engineering. So we are also excited about this. So thank you, and Tonda, please.
Okay, thank you very much for your introduction. So my name is Antonin Vobecky, and I will present you actually 2 of my works that I developed during my PhD here in collaboration with fellow AI teams in Paris and here in Prague. So the first work is called Drive&Segment, and it was presented at ECCV 2022 as an oral presentation. So as you might know, the current semantic segmentation models require large amounts of manual annotations. For example, to annotate a single image with semantic segmentation for the ACDC dataset can take up to 3 hours of manual labeling, which brings us to our method, which we developed for the case of unsupervised semantic segmentation, and we call it the Drive&Segment. So in this method, our goal is to learn image semantic segmentation in urban scenes without using any manual annotations at all. just by exploiting the raw data from cameras and lidars that are synchronized within each other. This is actually very important and useful in the automotive industry, where there are large volumes of unannotated data, and the recordings would be extremely costly to annotate by hand. Here on the left-hand side, you can see the inputs during the training to our method, where we have synchronized lidar and image data. And we would like to emphasize that we only use the lidar data during the training, as you can see on the left-hand side, but actually during the inference on the right-hand side, as you can see it, we only work with images. On the right-hand side, you can see the output of our method, which is some kind of pseudo-segmentation, which means that we do not have the knowledge of what the individual classes that we actually find, what do they mean. We just know that the same classes, denoted with the same color, they belong to the same category of objects, but we actually do not know whether it's car, pedestrian, and so on, but we can easily do this in the post-processing step. So our method consists of three main stages. First is the cross-modal extraction of object proposals, where we take the input lidar point cloud and we use unsupervised methods to segment it. You can see the different segments in different colors here. Next, we project those lidar segments into the image, and further on, we densify and pad them to really have dense pseudo annotations in the image. In the second stage, we extract image features belonging to every such proposal that we get from the 3D, and we group them by simply using k-means clustering algorithm that actually works very well if you extract features just as we do. This gives us some pseudo training data that we can then use for our final training of the model, where we propose a new teacher-student model that actually also integrates the spatial constraints from the 3D lidar scanner. To evaluate our method, we use 4 different datasets. They come from the standard daytime scenes, ranging through the night scenes, snow scenes, fog, rain, everything. And we just show here that we reached the state-of-the-art results. Here you can see the results applied to the Sivic dataset. On top, we have some videos where we apply our method on per-frame basis. And in the static images in the bottom, you can see that our method, without any manual supervision, can actually segment even thin structures and small objects. So next, then building on top of this work, we developed a new approach, which is called 3D. It was published at the just last month at the NeurIPS 2023 conference, which is the largest conference in machine learning. And we also worked on this project within the European project called Exa4Mind, where we are one of the partners. So in this work, our goal is, given inputs around the images, to output a 3D voxel representation that contains information about the space occupancy around the car. And also this occupancy field can be queried by text to obtain semantic information. So we aim to solve 2 tasks, as we show. The first one is zero-shot semantic occupancy segmentation, where we really take the 3D field, we specify the class names, and then we assign to every occupied voxel in the 3D space the class with the highest similarity between the text and our feature field. And the second one that we support is text-driven 3D retrieval from cameras, where the user just provides the input surround view images and the object they want to find, and we retrieve it in the 3D, just based on the cameras. So the advantage here is that it is really open vocabulary. You specify the classes by text. It's not limited. So you can, for example, use this tool to search for some corner case situations. But the problem is with the ground truth data for such tasks. If you want to be open vocabulary, then there are no such data, and in general, the data are very expensive to obtain manually. Also, these annotated data sets, if you already have them, all come with a closed vocabulary, meaning that they can only be trained to segment some predefined number of classes. And this is problematic, as one might like to search and detect some corner case situations, just as you can see on the right-hand side, and you wouldn't be able to do this with a closed vocabulary. So the contributions of our method are as follows. We first proposed a new architecture for this open vocabulary semantic segmentation occupancy prediction. We developed a tri-modal self-supervised learning algorithm where we leverage 3 modalities. The first one are images that we use both during the training and testing. Next is image that we use only during the inference to specify the classes we want to find. And finally, those are the light point clouds that we use only during the training of our methods, and again, we don't use them during the inference. In this slide, we show the qualitative results of the zero-shot semantic segmentation, where on the left-hand side, you can see the inputs to our method, which are 6 surrounding images, and on the right-hand side, you can see the outputs. Here we have one more example where you can, for example, see on the right-hand side that we can correctly detect and segment, for example, the bus in the image. And finally, here we show 2 more examples for the task of 3D retrieval task. For example, here for the case of black hatchback, which you can see on the images on the left-hand side, and it is retrieved on the right-hand side in the 3D. Here's the final example of the stairs that we can also somehow detect in the 3D. Okay, that's all from me. Thank you very much for your attention. If you have any questions, please ask.
Hello, my name is Antonin and I'm a first-year PhD student supervised by Josef Sivic, and today I'm going to present the result of our collaboration with Loschmidt laboratories in Brno and also at the Institute of Organic Chemistry and Biochemistry, which is there just across the road. And so, as you can see, my talk is going to be about designing protein-protein interactions. So we'll start with what they are. So in this beautiful animation, we can see how coronavirus attacks a human cell. So first of all, we can see that coronavirus has these trimers, and which are visualized in orange. And in fact, each of these trimers is composed of 3 proteins, which are kind of stick together. And we can see that coronavirus uses these spikes to attach to another kind of proteins, which are visualized in purple. And these proteins are receptors of a human cell. And so another type of proteins that we can see here are in blue, and they are called antibodies, and they are produced by the human organism as we can see to block the spikes of coronavirus, so it cannot attach to receptor and get inside. And so this is not some special case of a system which is abundant with protein-protein interactions, vice versa. Interactions between proteins or protein-protein interactions underlie many the treatment and development of many other diseases, such as, for example, stroke, cancer, or Alzheimer's. And so our colleagues, in terms of the stroke Brno consortium, developed drugs against stroke. And as we can see, stroke is essentially a medical condition when a blood vessel is blocked. And our goal is to break it down, to dissolve this clot, to restore normal blood circulation. And what we can do is to use the staphylokinase protein. So we can put this protein into a bloodstream, and then it interacts or attaches to plasmin, which is another protein which is present in blood. And when these 2 proteins are together, so together they help to break down the clot. And staphylokinase is a very attractive thrombolytic drug candidate. It's known for its high, so it's much cheaper than state-of-the-art thrombolytics. It's also significantly more safer, but it has a problem. So it doesn't really want to interact with plasmin as much as we want. So it's our goal to solve this, to make somehow staphylokinase more attracted to plasmin. And so if we take a closer look at this problem, so first of all, we can see that proteins are in fact large molecules, and more specifically, proteins consist of building blocks, which are called amino acids. So for example, 3 of amino acids of the staphylokinase protein are highlighted there. And so there are 20 this kind of building blocks or amino acids which exist in nature. And that's why what we can try to do is to kind of replace, or technically speaking, mutate these amino acids and trying to achieve what we want, so that it's more attracted to plasmin. And so as you can see, it's a combinatorial problem. And if we, for example, just focus on these 3 building blocks or amino acids, it's already 20 to the power of 3 solutions. And moreover, it's not only highly combinatorial, this whole system is dynamic and highly flexible. So it's really hard to somehow exactly calculate or predict the effects of such mutations. And that's why what we can do is to employ machine learning to help us in this. And so traditional machine learning approaches rely on annotated data, which contain examples exactly of this kind. So we have some protein-protein interaction and then some known mutation or this substitution of amino acid building blocks. And then we basically know whether it's good or bad. And experimentally, it's really hard to obtain this data in a wet lab. So that's why these data sets, as we can see, are limited. So at most hundreds of interactions and only thousands of mutations associated with them. And so our idea is to break down this limitation, because obviously it's really hard to imagine that we can solve such a complex problem from such a limited data. And so our idea is to inspire by the breakthroughs in computer vision or natural language, and to employ what is called self-supervised learning from a lot of unannotated data. That's why what we did in the first step is that we basically mined all the protein-protein interactions that humanity knows publicly up to date, and we created this large data set of unannotated protein-protein interactions. And as we can see, it's several orders of magnitude more training examples than in annotated data. And what we do in the next step is that we developed a self-supervised transformer-based model, which can really leverage our large data set of protein-protein interactions. And so during this first phase, the pre-training phase, we sample protein-protein interactions from our data set, and then we do something similar to natural language, we also recently employed in computer vision, that we mask some of the building blocks or amino acids, and we train our model to predict or reconstruct the missing ones. So basically to maximize the likelihood of the native amino acids. And only after that, we make a short fine-tuning on the small annotated data that I just showed on the previous slide. And so essentially now on the input, we also know some information about mutation or substitution of building blocks. And then we can intuitively predict the effect of some substitution by comparing probabilities of the native amino acid and the mutated one. And so as a result of our large-scale self-supervised learning, we achieved quite promising results. So first of all, we achieved state-of-the-art on standard mutational data, and we also confirmed that our approach can identify already known favorable mutations of staphylokinase and also a coronavirus antibody. And so in this, here we can see a photo from Brno. So in these freezers, we have protein, our designs or modified staphylokinase proteins, and we all keep our fingers crossed for the ongoing validation in a wet lab. Thank you very much.
Any questions? No? Thank you. Košnar, you are the next.
Yep.
Hey, I'm Bursuc. I'm leading a small research team that is part of AAG. Going to talk about 2 papers, one published at Europe's in 2020 and one published at IEEE in 2023. Both are top conferences in machine learning, respectively, computer vision. And both papers are on the 3D reconstruction problem. So let me introduce this first. The idea is that we are given a set of images. We know where they were taken in the world. We know the function that maps 3 points to pixels in the image. And we would like to build some 3D model of this. Traditionally, this has been either a point cloud or some mesh-based representation that can then be rendered very efficiently. A few years back, people started to look into representing the scene through the weights of the neural network. A very popular family of works are so-called neural radiance fields. So what you see here is not real images. These are renderings from a 3D model reconstructed images. You can nicely see that these approaches are able to recover reflecting surfaces, refractive surfaces at a very high level of detail. And this whole thing, these neural radiance fields, are actually based on something that was published about 40 years ago, which is called volume rendering. The idea is that if you have a volume of the scene and you would like to render this image, then for each pixel for which you would like to have a color, you shoot a ray through that pixel. You sample points in the volume gives you a color and some density that encodes, am I close to the surface or not? And then you can just accumulate these colors and get a final color for your pixel. The nice thing about this is, which was what people noticed about 4 years ago, that this whole thing is differentiable. So rather than assuming that we're given a volume and we want to render images, we can solve the inverse problem, which is we're given images and we would like to compute the volume that gave rise to them. And that's essentially what neural radiance fields are. So you're given a set of images, you try to learn weights in neural networks so that volume rendering reproduces these images. These neural radiance fields work very well for small scenes or for scenes that are very densely covered in images. But as soon as you go into more complex scenes where you observe each part of the scene by only a few images, things start to break down. So here what you should be seeing is some skull, some room with furniture in it, and a larger auditorium. You can see that this is not really what was reconstructed. And the reason is that they are reconstructed from few images, and the underlying problem is inherently under constraint. So there are many solutions that explain the images, but do not produce valid geometry. And in this first work, we noticed that there's a very simple approach to reduce this issue, which is based on the observation that nowadays you can train neural networks that take a single image as input and then produce a depth map, so some estimate of how far away each pixel, like the 3-point belonging to each pixel is from the camera, and you can get surface normals, meaning how the surface is oriented with respect to them. And these depth maps and normal maps that you get are inherently noisy. They have problems, but they provide reasonable priors where things should be in this. And that's what we are exploiting in this. And it's fairly simple to integrate this into one of these neural radiance field pipelines. So as I mentioned before, the way that it works is that you have an image, you want to get a color for that pixel, you shoot an array, you sample points along the array. Each of these points goes into neural radiance field or some representation of the scene. Out of this, you get a distribution of colors that's along the array, which you can integrate and get like a rendered image. And the standard formulation just compares this rendered image against the real image that is used for training. What we did is we added two loss terms that said the depth set we get from this rendering process should be similar to the depth set we get from the network, and similarly the same thing for the normals. So very simple thing, relatively easy to implement, but you see that the impact is quite drastic. So here you see that we go from some strange blob to actually being able to recognize the object, from some strange blob to actually being able to see how the scene looks like where furniture is, and also seeing more details of this reconstruction of the auditorium. This thing is, if you want to play around with this, is part of the SDF Studio library, which seems to be popular on GitHub. It has been starred 1,800 times, which is kind of the GitHub equivalent to a citation of the paper. Okay, so this was the first paper. Let me switch to the second one, which is called TEPRANER. This is joint work with Jonas Polhanek, one of my PhD students. Couldn't be here today because he's visiting ETH. The way that the standard nerves are typically represented is that you subdivide the scene into voxels, volumetric elements, and then for each corner, you store some learnable vector. And you learn these features that are attached to the corners during training. If a ray passes through a voxel and you would like to color for a point, you essentially figure out, you do a trilinear interpolation from the features that are stored at the corners to the 3D point, and then you feed this feature into a neural network that gives you color density. The reason why people use voxels are these voxel-based representations are much faster to train than just representing whole scenes through neural network, like orders of magnitude. But at the same time, you also need more memory. And you have the problem that this voxel grid does not necessarily align with the geometry of the scene. Actually, a lot of voxels end up being in space that you're not interested in. So if you imagine like placing regular voxels over in this auditorium, then a lot of these things will actually end up in the thin air and you don't care about them, but you still need to store them. And in this paper, we try to tackle the problem of having a representation that better aligns with the scene geometry. And it's based on the observation that typically you don't only get images, but you also get some prior of the 3D scene in the form of a sparse point cloud. And you can use this sparse point cloud to compute a volumetric representation using, again, simple concepts from computer graphics. There's this thing called the long A triangulation, where you try to compute a set of triangles that fits your points and satisfies a certain set of properties. And these points in turn define tetrahedra, so you get a continuous volumetric representation of this. And the nice thing is that here, these tetrahedra adapt nicely to where the surface is, because the corners of the tetrahedra are 3D points that are on the surface. It's also adaptive in the sense that you typically get smaller tetrahedra closer to the surface and larger ones far away, so you don't really spend much of your memory budget on parts of the scene that are not interesting. At the same time, it's super simple to integrate them into the standard pipeline. So as I mentioned before, for storing voxels, to get from features of the corners of the voxel to a point, you do trilinear interpolation. For tetrahedra, you do barycentric interpolation. It's actually a bit easier to compute. Here's an example of comparing this tetrahedra-based representation against a dense voxel grid, and you can see this is for about the same number of learnable parameters, same memory consumption. Because we are actually spending our budget wisely close to the surface, we get much better results. Here's an example on the real world, a more complex scene. This is not a video, this is rendered images, and this is the underlying scene geometry. Depth maps are cold colors, so blue means closer to the camera, warm colors mean far away. And you see that we are able to actually accurately recover the point structure. The whole thing is freely available online. It's integrated into a large library for learning neural network, neural radiance fields, and I think it's gaining traction. So these things work typically well in smaller scenes. We're now starting to look into larger scenes. So this is the inner city of Aachen, reconstructed from images and the stepper method. And yeah, that's all from my side. Thank you very much.
Hello, good afternoon. Okay. So my name is Victor, and today I'm going to finish up the presentations from the RMP group by presenting two CVPR papers from the Applied Algebra and Geometry group led by Thomas Feidla. So the first paper presented at CVPR 2022, the authors there, which I was not part of the paper, the authors there they combined trivial machine learning with algebraic techniques to solve minimal problems in computer vision in order to significantly speed up a specific minimal solver for a specific minimal problem. And in the second paper, we took specific minimal problem, which was algebraically hard and couldn't be solved with the techniques that currently existed. We showed that this problem can be decomposed into simpler sum problems such that they can be later solved consecutively using the techniques that currently exist. So first I will start with a simple intro into the 3D reconstruction from the images. The 3D reconstruction is important since it can be later used for visual localizations or as models in computer games. So in this slide, you can see a 3D model of the reconstructed statue of the dragon, together with the positions of the cameras that produce the images of the dragon. So I will later talk about minimal problems that very often arise in the 3D reconstruction task. And first, before explaining what they are, I will first like to motivate them. So in this slide, you can see a 3D reconstruction pipeline, and the motivation is exactly that the minimal problems are part of the 3D reconstruction pipeline. So the pipeline is basically divided into four steps. In the first, we produce the images as the input to the pipeline. In the second step, we find the image matches. It can be point matches or lines matches that correspond to the points and lines in space that are observed by the images. And in the next step, that is the most important step for us, and what we actually study very closely is take the image matches and compute the relative camera poses that produce the images. Inside this step, the minimal problems are being solved thousands of times in the ransack-based optimization, and it means that it is important to have very efficient solvers for such minimal problems. So what is a minimal problem actually? I will explain it on a simple example of estimating the parameters of a 2D line from the point measurements. If you imagine just one random point from a 2D line, then there are infinitely many lines that pass through that point. You can imagine a whole infinite array of lines. If you take two random points, then there is exactly one line that passes through each of them. So it is sufficient to take just 2 points to estimate the parameters of the model in this case. If you take, for example, 3 or more points randomly, then there is no line that passes through all of them. However, you can obviously use some other optimization techniques to compute the parameters of the model. However, this is not what we are dealing with. We just take the minimal amount of data, namely 2 points in that case, because it leads to a polynomial system. Like in this case, these are linear equations that has finitely many solutions. And the reason why we do that is because we have very efficient techniques that can deal with such polynomial systems and that can find the solutions to these polynomial systems very efficiently. In this slide, you can see 2 examples of minimal problems that arise in computer vision. On the left-hand side, you can see the famous 5-point problem, which is the point of estimating the relative pose between 2 cameras from 5 points. And on the right-hand side, you can see another minimal problem from the huge, actually, zoo of all different kinds of minimal problems, which which considers 3 cameras that observe 4 points in space. The first problem actually generates a system of polynomial equations that has 10 solutions over the complex numbers, and the one to the right generates another polynomial system that has 272 solutions. The number of solutions is the rough measure of the complexity of a polynomial system. However, we are only interested in just one physical solution that corresponds to the real situation. So in the first paper, authors used trivial machine learning to actually speed up the minimal solvers, to show how the minimal solvers can be sped up even if the number of solutions is very high. So a minimal problem, actually, it relaxes the original geometric formulation of the problem, because it also removes some algebraic inequalities from the formulation, and due to that, the number of solutions to the polynomial system increases. Such polynomial systems, there are different techniques how to solve them, and one of the techniques is to apply homotopic continuation, which takes the solutions that were pre-computed to the sum. Another instance of the problem, and we track each of them to the new solutions of the problem that we would like to solve. However, since in minimal problems we are just interested in one physical solution, we don't need to track all of the 272 solutions, like for example for this problem. We just can take one physical pre-computed one, like here, and check just this solution. So, and that's what the authors in this paper did. So what they did is, it is enough, actually, they say it is enough to pre-compute the problem solution pairs for sufficient number of instances of this problem, and then learn a model which, for a given problem, the one which we would like to solve, we would like to obtain a model which would generate a starting problem solution pair from which we would homotopy conjugate to a solution, to our desired solution. So that's what they did, and that's how the network looks like. It is a very simple neural network which contains 7 layers. It's the 7-layer perceptron. I don't know much about this, about machine learning, actually. So it is a very simple network. That's the message, and it outputs the starting problem solution pair from which they homotopy continuate by applying some corrector predictor steps. This is what homotopy continuation is all about. So, and that's actually was where they gained the speed up. So they compared their results with the previously implemented solver for this particular problem in 2019. They validated it on a data set from ETH 3D dataset, and they observed that their algorithm takes 10,000 less time than it took for the algorithm implemented before. So that's the result. And the second paper, which I would like to describe, is our paper presented at CVPR 2023, where we took another minimal problem in computer vision that consisted of 4 cameras that observed 13 points in space, which was algebraically very hard to solve using some specific numerical symbolic solvers of polynomial systems. We have shown that we can decompose this problem into simpler subproblems such that they can be solved using the techniques that currently exist. And first, I would like to very basic intro to decomposing polynomial systems. I would like to explain it on an example of the 5-point problem in computer vision. here we can see one of the formulations of this problem, which has 20 complex solutions. So the unknowns in this formulation is the relative rotation and translation between the two cameras, and the depths of the 3D points as well. Well, we can eliminate the depths and we can obtain another formulation of this problem, which still has 20 complex solutions in RMT. However, when we make specific substitutions in this equation, then when we introduce the essential matrix E, then we suddenly obtain another polynomial system which contains 10 solutions over the complex numbers. And it indicates that the new polynomial system on the right is simpler to solve. So that's why we're interested in decomposing polynomial systems there, so that we later gain a speed up in the solution. So how could we, given a specific polynomial system, how could we say whether it can be decomposed or not? So there is the whole theory, which I cannot really, it is very complicated. It's based on some concept which is called the monotropic group, which is some numerical technique which kind of collects the permutations of the solutions. Here you can see the animation. Here is the parameter space. We can the loops in the parameter space and track how the solution changed. And this gives us some group called the monodromy group, from which we can compute its fixed partition set, which we observe here. And we can see there are 10 blocks of size 2, which means that the solution with the 20 solutions, the formulation with the 20 solutions can be decomposed into two formulations with 2 and 10 solutions. So that's just some magic happening here. So what we did, we took some problem which maps the 3D point to a radial line, so our cameras are radial. Here is actually the polynomial system which arises from it. The unknown is the world point, and the radial lines in the cameras are known. After fixing the world in the first camera, we obtain a polynomial system with finitely many solutions, and we check with the monodromy that the number of solutions is 3,584, which is too high for symbolic numerical solvers in computer vision. So we would like to actually see if there are some decompositions in order to relax this problem, in order to obtain another sequence of simpler polynomial systems from it, such that it can be solved faster. And here we observe that such a decomposition indeed exists. And this is the product. Basically, this number of solutions decomposes into a product of numbers like this, and these numbers correspond to simpler polynomial subsystems, which can be solved and can be solved efficiently. So there is a significant speed up, which takes us from 21 seconds to 0.014 seconds. So this speed up is significant, and that's the reason why I look for the decompositions. It's in this slide you can see just an example of the 3D reconstruction. So we implemented the solver and we verified how it works on the real data. Here you can see an example of the 3D reconstruction of some cores. And so that's it from me. Thank you.